So it's a pleasure to have Professor Alvadi Ganesh today for our seminar. So Ganesh is an associate professor in the School of Math in University of Bristol. His research interests include large deviations, random graphs, game theory, and decentralized algorithms. He has won many awards and honors, including 2005 Informs Best Publication Award and 2010 Metrics Best Paper Award. Today he's going to share his research on multi-agent mathematics without further ado. Thanks, Devon, for the kind invitation. Introduction and Devon for the invitation to Columbia Tech and to speak on the seminar. So today I'm going to speak about multi-agent, multi-arm bandits. This is based on joint work with several people. It started when I visited Sanjay at UT Austin. And worked with a couple of PhD students there, and then in back with at Bristol with my colleague Henry Reed and a joint student Colin Reed. So I'll give an overview of a few different papers in this work. And I just wanted to say at the start, we'll go at I don't have a lot of slides, so feel free to interrupt, ask questions when you like. There's not a lot to rush through. Okay, so I'll start with motivation and some preliminaries, and then I don't assume that you are all experts on Bandit, so I'll give a review of some bounds and results, what's known for a single agent, and then we'll go on to the multi-agent setting, and then I'll specify the model we are looking at and give a somewhat more formal statement of the problem. Then I'm just going to state the main results. We won't go into details of the proofs, but just very briefly sketch some of the ideas behind the proofs. And then I'll conclude with related work. Okay, so a slightly frivolous motivating example. You want to find the best restaurant in Atlanta. Okay, so let's say this notion is well defined. There are many things you can disagree about the whole model in this setting, but it's a nice way of introducing many of the model assumptions, which are indeed quite strong. So in this case, implicitly, I'm assuming that we all agree on the ranking of the restaurants in Atlanta, which of course is not true. We all have different preferences and tastes and computers, but let's assume that's the case. So there is such a ranking, but we don't know it. And we are also going to assume that not only can we rank, we can assign numerical values on which this ranking is made, which are consistent with this ranking. So we can assign a numerical score to every restaurant. And so sometimes we might be able to rank things, but we might all have different scores, scoring schemes. You can see this with marking exam scripts, I guess. Some people are stricter than others, but they may quite likely agree on the ranking. So we assume we are all at the same scale. Okay, but also the restaurants differ from day to day. You can have a better or worse experience on a particular day. So you don't get always the same score, but you get an outside version of a true score. Okay, that's the same. Okay, and now, of course, there are a lot of restaurants in Atlanta, so you can't visit every one of them and find the best. So what would you do? You would visit a few, you have your own ranking, you exchange information with your friends, you make suggestions to each other. And so that's what we do in practice. So how well does that do? Is that enough for us to identify the best, and how quickly can we do that? So that's the kind of question we are interested in. Okay, so maybe an example that's actually used in practice. So you have websites display ads in response to search terms or keywords. And then, so you want to decide what you should display in response. In practice, I believe now this happens in a very centralized way. Google or Microsoft or whoever gathers all the information on click-through rates on ads in one place and makes decisions based on that. But one could imagine that that maybe this is not the best way to do things, and given that you have a huge number of terms, a huge number of ads, but also lots of servers in different places, maybe we can do this in a decentralized way by sharing information. Okay, some other examples that also happen in practice, you might want to decide which route are you going to choose to commute to work. When you're in a new place, you try out a few different things, you gain experience of what's the way. Purchasing consumer goods, we all rely both on recommendations that people we know and also on reviews on sites to make these decisions. So again, we are solving problems in these settings. So you can ask two kinds of questions. You can ask, how should we make optimal decisions? And that's what I'm going to address today. That's maybe more the ORCS type of question. You could also ask, what do agents actually do? How do human beings behave? And that maybe is the question more of interest to economists and social scientists and so on. Both are interesting questions, but we'll only address the first one. Okay, so now let me start by introducing the classical multi-arm bandit problem. So you have a collection of actions or arms to choose from in terms of our motivating example. These are the different restaurants. Time is discrete, and at each time step t, you are going to choose one of these options and try it out, and you'll get this random reward xit. Okay. And the assumptions are that at successive times you play an arm or take an action, the rewards you get form an IID sequence. And also when you play different arms, the rewards you get from them are mutually independent. Okay, and you only observe the reward for the action you play, and you have no information about other actions. And so the goal is to decide which action to choose in each time step, and you can make this decision only based on the information you have, which is the past choices and the rewards you observe from them. And what's the objective? The objective is to minimize your regret. And how do we define regret? We look at the expected difference between what you would have got if you had played the best arm and the expected reward you got from the arm you actually played. So we look at expectations, and we want to minimize long-run regret. And so this involves a trade-off, which you're all familiar with, I guess, between exploration and exploitation. So the idea is you want to try out different things to find out which is the best option, but if you spend too much time trying them out, then you don't have enough time to exploit the best decision and get a large reward. So you have to decide how much exploration to do. And this may be familiar, but if you're seeing this for the first time, I also wanted to emphasize that regret is defined with respect to expected reward and not with respect to something. So if you like, there are two kinds of uncertainty in the problem. There's aleatory uncertainty, the randomness in the outcomes, and there's epistemic uncertainty, what you don't know about the arms. And we are only dealing with when using the epistemic uncertainty. There's nothing we can do about the aleatory uncertainty. Okay, so let me review what's known in the single agent setting that we just studied. So in today's talk, we are going to look at the simplest case of Bernoulli rewards, though many of the results can be generalized to very straightforwardly to sub-Gaussian rewards and maybe. Sub-Gaussian cases should be straightforward. So we have so each arm gives on successive plays gives independent Bernoulli rewards with parameter mu I for I. So you get a reward of 1 with probability mu I 0. And let's say we have ranked the arms from the best in decreasing order. And the gap between the best and second best arm is going to play a role in some of the results, so we'll denote that by delta. So the regret up to some time t is what you would have got if you had played the best arm in every time step, which is mu1 times t, minus what you actually played. It is the index of the arm you actually played at time step t. So this is your regret. So we want to know how well can we do? Are there fundamental lower bounds on what you can achieve based on how much information you can gain? How quickly? And then are there algorithms which actually achieve what's the best achievement? Okay, and there's a very classical theorem of Nye and Robbins, I think from the 60s. Quite old, where they show that for any reasonable algorithm, the regret is at least this much. So for each arm, except the best, you look at the difference between the mean rewards of the arms. Okay, so firstly, it scales logarithmically in time. So that's one of the key insights. The scaling in time is logarithmic. And the prefactor is the sum of all these terms, one for each arm. If mu I is much smaller than mu1, you suffer a large regret every time you play it. But if mu I is close to 1, the regret at each play is small, but it's hard to tell them apart, so you will end up playing them a large number of times. And there is suboptimal around a large number of times, and so you have stuff. And KL here is the relative entry. So this determines how well we can distinguish the two arms and decide which one is better. Okay, so this is the main expression to keep in mind. And if the gap is small, then the KL divergence roughly looks like the square difference up to some constant value. Okay, so that's a review of results that we already known to most of you. And there's also an algorithm which achieves the correct log t scaling called the UCP algorithm or upper bound algorithm. So here, okay, so how does the algorithm work? So what it does is it calculates an index for each arm. The index is based on how many times you played that arm, what's the empirical mean reward you observed up to that time, and some parameter. So the index is large if you observed a large empirical mean reward. But if you didn't play it too many times, there's more uncertainty about what the reward might be, and it boosts the index based on that. And okay, so there's this magic scaling factor square root log t, which comes into it, which comes out of the analysis. So it's not obvious why we should choose this thing, but I guess there's some intuition for why you should pick something with big mean reward and something you've not played too many times. So those bits I need. Okay, and how well does the UCP algorithm do it? It does achieve the log t scaling, not with the best constant, slightly worse than the best possible constant from the Lion-Robbins bound, and there's a slight variance that goes on which does achieve the best constant. And this is all in the frequentist setting. There are also similar things in the Bayesian setting. So there's an algorithm known as Thompson sampling, which you may be familiar with, which also achieves the log t scale. Okay, so now let's move on to the multi-agent setting, which is what this talk is about. So this is first. So in many practical situations, the number of arms k is very large. And then if you look at your regret expression, there's a sum over k of terms, the difference between u1 and ui. So if k is large, you are going to get regret. But you may also have a large number of agents. And then you could maybe somehow split the exploration task between the agents in such a way that you get much better regret bounds on that basis. So that's the idea. Okay, and the agents can communicate over some graph, maybe the complete graph, maybe something else. And again, the objective we are going to look at, just to be precise, is to maximize the aggregate, maximize aggregate reward or minimize aggregate regret over all the agents. Now, you could say maybe this is not a good objective. You should also care about individual agents. It's not great if you minimize the aggregate reward, but minimize the regret, but all the regret is suffered by one agent and everybody else. We don't actually put that into the optimization problem we pose, but from the solution, you'll see that all agents get pretty good regret.
So this graph is only among the agents. There's no graph between the arms and agents.
No, okay, it's only. So,
do the agents know the graph structure? Or they communicate only with their neighbors?
For our algorithms, they don't need to know the graph structure. The analysis requires the graph structure, but the algorithm doesn't. Okay, and so let's say that at each decision epoch, an agent place an arm, and they can choose to communicate or not with their neighbor. Only with one of their neighbors. So if you're on the complete graph, for instance, you're not allowed to communicate with all your neighbors, but you pick any one of them and you can talk to them. Okay, and the communication should be too long. You shouldn't be allowed to say your entire history of what you observed. Okay, and again, in this setting, we want to ask, are there fundamental lower bounds and are there good algorithms for achieving this? So let's look at two extreme naive bounds. So at one extreme, we could assume the agents don't communicate at all. They just do their own thing. And in that case, you just get the Lion-Robbins bound or the regret per agent regret, and then n times that. Okay, and there are algorithms for achieving this, essentially. So using the individual KLUCP algorithm, for instance, you can get this regret per agent and n times that over all the agents. So k is the number of arms, n is the number of agents. Okay, and the lower bound on regret, the other extreme, let's assume there are no communication constraints, you can communicate everything, then effectively it's like there's a single agent who has all the information. So then in the first t time steps, there are n agents, so there are nt place of arms. So it's the Lion-Robbins lower bound of what you get with one single super agent playing this nt times. So the n was outside here, it's gone into the logarithm. So effectively, there's a factor of n gap between these somewhere. So there's a huge gap between not communicating at all and communicating everything. So where can we get to with limited communications? How close to this can we get with limited communications? That's the question. Okay, so when we started working on this with Abhishek Sakararaman, so the first result we were able to get was, yeah.
It's not immediately clear to me why the log NT.
The previous slide.
Yes, for the following reason. The agents can communicate anything that they want, but then when they make an action, are they all supposed to make the action at the same time?
Okay, there's a slide that. Yeah, you're right. So, okay, so it's not obvious. So in each time step, maybe are they making an action simultaneously? In one particular time step, it doesn't matter. From previous time steps, they would have gained all the information, so it won't change things. But if you prefer, think of them as making actions sequentially even within the time step and receiving information from other agents. That's the best possible case. So in that best possible case, this is what you can do.
Thank you.
Okay, so the first bound we were able to establish was the following. So you have the log t term as before, so at least we get logarithmic scaling in time. If you did the usual UCP analysis, there would just be the k over delta term. There's this extra term coming from the number of agents. So not just the number of arms, the number of agents also comes into the bound. And then there's a constant bound as well. This doesn't scale with time, but there is a fairly large constant recurrent U income. So the typical scenario we are interested in, the number of agents is around the same or smaller than the number of arms, maybe scaling linearly or sublinearly in the number of arms. If that's the case, then this bound is, if n is the same as k, there's an extra log n term, so you are within log n or polylog n of optimal. Yeah.
Another thing that is unclear to me, sorry, I may have missed this when you transition. The slide before, there was no communication restriction among the agents.
Yeah.
On this slide,
on this slide, we propose an algorithm with very limited communication, which I haven't told you the algorithm, but we are looking at algorithms which have very limited communication. So I propose this constraint that you only communicate maybe once per round per agent and a limited amount of information.
so every agent can still communicate with every other agent?
Not
Is
per,
that what the, okay, then I don't understand what the complete graph is.
no, not per round. It's able to communicate with all other agents directly, but in each round you have to pick only one of them to communicate.
Okay, I see. Thank you.
So with no communication, you were getting factor n. So if I were to think of that in terms of your first term here, that's n k over delta log t. So you're trying to separate the k and n. Is that the goal?
Yeah.
Okay.
Yeah, so we've got rid of a multiplicative n in front of the k, and it's become k plus n log n instead of nk. So that's the first improvement. Yeah.
Is there a tighter lower bound known in this slide than the one that you presented in the previous slide? Because there you had n inside the log, now you have n outside the log. So what is
So
what is the
we are okay. So the n inside the log. So you can split this. So we are separating the n inside the log goes into the constant term, and so there is a log t term. The coefficient on the log t is essentially k over delta here. And then there's a constant term which is log n over delta, or k log n over delta, k log n over delta. So the coefficient on log t instead of being k over delta has become k plus n log n. And the constant term instead of being k log n over delta has something somewhat worse.
So I guess my question is, so if I just focus on the first term, there is the additional n log n, and is that inevitable or can it be improved?
It can be improved. So in subsequent work, we improved that. So this was our first result, yeah. So, and then in follow-up work with Ronshi Chawla, we also then considered more general graphs. And then this matrix P tells you the probability with which you are going to communicate with different neighbors in each time step. And then the conductance of this probability matrix plays a role in the bounds we get. Okay, I'm not going to define conductance very explicitly, but you can think of it as a measure of how well communication spreads through the graph. So if it gives kind of lower bounds on the rate at which one subset of nodes communicates with its complement over all possible subsets. Okay, and then we looked at another algorithm and we got the following regret bound. So we have the log t now just gets multiplied by k. There's no n log n term here. And then the constant terms also look better. And then the conductance plays a role in the constant term, but not in the log t term. Yeah.
There's another thing that I can say. Sorry? That my intuition doesn't get. So I'm looking at how the delta appears in those bounds. And if I make the delta very, very small, I'm essentially making the arms almost identical. My intuition would be if the arms are almost identical, my regret should be very, very small. But then in the bound, I have 1 over delta.
Yeah.
And that's where my intuition is broken, because now it's saying if the arms are very, very identical, the regret bound becomes infinitely large.
Yeah, that's true, but that's what happens in Bandit. So because the difficulty of distinguishing between the arms is 1 over delta squared. So you incur a very, very small regret every time you play the wrong arm, but you have to play the arm 1 over delta squared times in order to know for sure which is the better arm. So you end up incurring regret. So it's kind of odd.
So if I can add a comment.
It's very clarifying, thanks.
So if they're very close by, then the regret scales as t, even though the coefficient is very small. Let's say the top 2 arms differ by 0.01, then the regret is 0.01 times t. But here you want log t. So if you want log t, then you get this 1 over delta kind of behavior where the constant is very big.
And so this graph, can you explain more? How does it restrict? How is it restrictive versus like complete communication?
So even on the complete graph, if you were choosing only, if you're only allowed to communicate with one other node at a time, you might, for example, choose this matrix P to be 1 over n uniformly. You are choosing uniformly at random who to talk to. So you can calculate the conductance for that matrix. It's a constant, maybe 1. So it's an order 1 term for good graphs. And yeah, so you can also ask for what graphs is it good. So for expander graphs in general, the conductance is good. And you can communicate with other nodes fairly quickly. But if you were, say, sitting on a grid or a cycle, then the conductance is small and it takes a long time for information to propagate from one end to the other.
So if P is like 1 over n everywhere, it's like effectively you have one single agent and you get this log nt, right?
No, it's not like, it doesn't become like one single agent. Communication is still restricted. You can only communicate a little bit. You can only communicate with one other person per time step. To make it like one single agent, you have to communicate with everyone at every time step. Tell them everything.
So, go ahead.
So I was wondering, is there any sub-modularity property in terms of the commutation matrix? Because you have this lower bound and this upper bound, and then there could, I don't know, my guess is there should be some submodularity in terms of when you increase the communication or decrease the communication constraints, you should have lower differences, right? Or I don't know, is it?
Good question. I don't know the answer to that. Maybe our analysis was not refined enough to capture that, but it maybe there is.
So for the result in the previous slide and this slide, is it the same algorithm or is it a different?
It's a different algorithm. It's a slightly different algorithm. Yeah, there was an improvement both in the algorithm and in the analysis.
Another quick question. There was a delta square in the additive term in the previous slide. So is there a delta square hidden here or?
Good question. I don't remember. There might be a delta. Yeah, some of the constants I have left out. Yeah. Okay, so and then there's one more paper to talk about, but okay. So on the log t term, we have this coefficient, and then there are some constant terms. And then we looked at this again later with my colleague and student. And then we changed the algorithm again a little bit. And then we got the scaling where the coefficient of log t now instead of 1 over delta becomes delta over the KL divergence. And this is the best possible. This is what your line robin. Other gates, not gate, there are ugly constants everywhere, which I've hidden, so and they could be large. So that is a fairly, the additive term is pretty big for our bounds, so you do get a large, maybe not in practice, but at least the bounds we can prove there's a large additive constant, but the coefficient on log t is the best possible. We do match the line robins. So that's the full story of what we did on this problem. Okay. And then I'll tell you a bit about the algorithm. I won't start with the first one. So in the second paper with Ronshi, this is the algorithm of that, which was a slight refinement of the first algorithm. So I'll explain this in some detail. So what we are going to do is there are k arms and agents. So we partition the arms into sets of around this size. And then we assign one set to each agent. So there is some pre-processing involved. So you have to agree on which agents take care of which arms. And these are the sticky sets. So this never changes. They have to keep these arms. But then there is an active set, which is this plus some additional arms, which they will get by talking to others. And then it's easiest to explain with examples. So we have 4 agents, 10 arms. I've started out assigning 3 arms per agent somehow. And okay, in some way, these are the other active arms they have acquired at some time. And inside the box is the sticky set. Okay, and then how is this going to evolve? So, so we are going to divide time into phases. And in each phase, the agent is going to play its active set and it's going to play UCP over this active set. And then, so during a phase, there is no communication. All the communication happens at the ends of phases. And at the end of the phase, it's just going to recommend it's the arm it played the most in that phase to a randomly chosen agent neighbor. And okay, similarly, it also, each agent makes recommendations. One recommendation, it may receive some random number, it may receive none. If it receives several, it just picks one at random. So it's going to take that extra arm from the recommendation, but the size of its active set doesn't grow. It has to evict something. So it evicts it's not allowed to evict anything from the sticky set, so it evicts the least played arm in the sticky set. And then the phases are not of constant length, they also grow in length and they grow polynomial. The jth phase is j to the power something. Okay, so an example of what happens, so at the end of a phase, maybe the circled arms are the ones that were played most often by that agent. They might be in the sticky set, they might be outside the sticky set. And these arrows tell you which way the recommendations are happening. Who's chosen whom to talk to. And then there are also these least played arms outside the sticky set. These are the things that are going to be evicted. This one got no recommendation, so it's not evicting anything. Okay, and that's the argument. Okay, so is the picture clear?
Like, I was wondering how your algorithm is, like, is it scalable in terms of n, or because you select only a subpopulation of this n, right? I just wanted to know like how your algorithm is scalable in terms of n.
So it's a distributed algorithm, right? So each agent does very little. It only has to keep track of k over n arms. Okay, so if k is n squared, maybe it's still fairly heavy, but it's still better than having to deal with all the arms, which you would otherwise have to do. So that way it's scalable. The communication is very scalable because these phases are growing long and you only talk once per phase.
Is there any reason why you evict an arm which is least played and not an arm which has the worst, which has the worst estimate?
Yeah, I guess you could do that. So it's just something we picked for the analysis, but I think it would go through with some other natural variants. But we had to pick one thing to analyze, I guess. So, and how does this differ from the first paper we looked at? So the main difference is there we wanted to make that even more distributed. So there was no coordination. Initially, people just picked their set of arms. So to cover all the arms, we assumed everybody picks at least log k arms or an extra logarithm factor. So you had a bigger set. We didn't evict arms. So here you have to have these sticky sets. So there's a small chance you might evict the best arm. You don't want that to happen. So here somehow every arm is kept by someone or the other, so that can never happen. There was no coordination, so nobody ever evicted arms. We relied on the fact that the number of arms grows more and more slowly because the phases are growing longer. And so those extra factors made the regret worse. So those were the differences. And then in the last paper with Reeve and Newton, the only change was to replace UCP by KLUCP. That was the main change. Okay, and then we also said you can shrink the non-sticky set down to one arm if the recommendation you receive is already in your active set. So you can get it to the minimum size. That was a small extra. Okay, so I just have 2 slides on the proof. There's only one main idea, and that is that gossip spreads quick. That's the key idea of it. So let me tell you about gossip. This has nothing to do with bandits. So let's say you have, so forget about bandits for the moment. We just have n nodes, n agents, and one of them initially knows the rumor. And time is discrete, and in every time slot, everybody who knows the rumor is going to randomly pick someone from this graph, let's say. For now, maybe you think of the complete graph. You randomly pick someone and tell them the rumor. Okay. How long does it take till everyone learns the rumor? And this was analyzed way back, I think in the 70s or 80s, by Grimmett and Fries, who showed that there's a constant times log n times logs. I think it's some constant, but they all learn it in some small multiple of log n times logs. And then it was Patel gave tighter bounds on the time. And Jansson generalized it to continuous time models instead of discrete time models. But in considerable generality, you basically have on the complete graph log n time slots. And if you look at other graphs, you have this conductance coming. It takes longer by an amount which depends on the conductance. And that's why that comes up in all.
This is an exact statement,
These are bounds,
like
upper bounds of the time. And there are constants, sorry.
for the graph case, is that tight?
Is that tight? No, probably not. It's probably not. Oh, yeah, okay. Wait, it's tight in the sense there are graphs you can find for which it would take this long. But on particular graphs, it may be a very loose bound. Yeah. Okay, so this is the idea. And then what's the sketch of the proof? So, okay, so we have to decide how we are going to make the phases longer. And the idea is that, so within a phase, you are just exploring within your set. You're playing UCB within, not exploring. You're doing exploring and exploiting. You're playing UCB or KLUCB within your active set. And at the end, you are going to recommend the most played arm. And the idea is if the phase is long enough, your most played arm is going to be your best arm. The chance of it not being your best arm is very small. And because the phases keep getting longer, the chance of making the wrong decision per phase keeps getting smaller. And you can choose things in such a way that Borel cantilly applied. So you only make mistakes finitely many times. So that's the main thing. And so there's some last time at which you ever make a mistake, and after that, any recommendation you make is always that of the best arm. And so we just press through the populations. And then, yeah, and then nobody, once everybody has got the best arm in their active set, that's all they are ever going to recommend, and nothing changes. So at that large random time, the system is frozen, everybody knows the best arm, and they are going to play UCB on their active set, which is of size k over n, and that's it from there. And that's and then you just base the analysis on that and do a standard bandit analysis after that. Yeah.
So the result is a regret result, which is a finite time result. So why does Borel cantilly show? It's a asymptotic. Borel cantilly is an asymptotic state.
So okay, so you can say that after the probability that you haven't reached this nice state by a certain time, you can take that into the bound and then say, so all that goes into the constant term, which is therefore very huge, and then on the log t scaling, which is asymptotic, you are just doing the gossip has stabilized the system, and you're doing a standard bandit analysis.
I have one more question. So if I just think of a single classical bandit problem, so from what you explained, it sounds like after some time I'll find the best arm and that's it. But I thought like you have to keep exploring forever.
Yeah. So you do keep exploring forever. Okay, so within your active set, you keep exploring forever, but you have the best arm has entered your active set and never leaves it after that time.
And that happens in finite.
That happens in finite. Random finite.
Right. That's nice. That's it.
And maybe one follow-up with Seva's question, like this is asymptotics with respect to t only. There is no asymptotic in n.
No. Or yeah. These are quite ugly bounds in n and k, but the asymptotic it's in okay. We also give explicit prefactors and constants, but they are very ugly. So I guess it is finite time, but it's maybe interesting only in an asymptotic sense. Otherwise, you would say this result is only of theoretical interest. It's practically useless. Okay. If you looked at the actual constants. Okay, but yeah, so that's the intuition, and it, so the constants may not look great in practice, but the algorithm is still there, we can simulate it, so we do that with 100 arms, 10 agents, 100,000 time steps. Okay, and so we look at, these are the parameters we look at, so we are going to take the best arm to have mean reward 9, and all the other arms have mean reward 0.8. So we look at the effect of how it grows or how the regret accumulates over time. Also, we look at what happens if you fix the final time horizon to be 100,000 and keep changing the arm gap, and how does the regret scale. And we also did some simulations on a few different graphs. Okay, so you can kind of see a log T scaling in all these plots. So at the top here is what we did with Ronshi, Sanjay, and Abhishek. So this is the gossip insert eliminate algorithm, and at the bottom is the improved algorithm with Newton and Reed. And there are two things that are changing. So part of the difference is between having one non-sticky arm versus two. That gives you a small difference in the improvement. The main improvement comes from changing UCB to KLUC. That's where the main gap is between these simulation results. So you get a roughly, at least for these parameters, you get a factor of 2 improvement by using KLUCB instead of using. And okay, whatever the constants may be, the bounds we can prove may be bad, but the constants don't look too bad in practice, at least on this problem. So those are the results we get, and then we looked at. So you look at the final regret after 100,000 time steps, but now you bring the arms closer together, and you look at the regret. Yeah, and as the gap between the arms gets smaller, the regret does grow, somewhat counterintuitively, it does grow. And again, the KLUCB does significantly better. Okay, and the gap increases as the problem becomes harder. That's what theory tells you as one should have. Okay, and finally, we looked at a few different graph topologies. So the complete graph is at the bottom. It has the least regret. And these two were somewhat surprising to us. The cycle does better than the star. We didn't expect that. Maybe what's happening is that the star in every time, at the end of every phase, gets lots of different recommendations, and and since it randomly chooses a recommendation, it's not picking up the best. I'm just speculating, we don't know, but we were somewhat surprised with this result that the star did worse than the cycle. We expected the opposite. Okay, and so that's the work. So I'll finish with some related work and some of the problems. So variants of multi-agent bandits have been studied. So Kolla, Jagannathan, and Gopalan looked at a model where there's no explicit communication, but you can observe all your neighbors as well as yours. So apart from the arm you play, you observe, you can see what your neighbors are doing and what reward they get. And you can use that information as well to make decisions. And so in the same way, the identity of the best arm diffuses through the graph because the neighbors can see them and then pick them up and so on. Okay, I've forgotten the details of this paper. So I think here they maintain some estimate for all possible arms, and they use some gossip-based averaging of estimates between agents. So it's a bit more heavy communication-wise than in our model. That's what we have. And then the Bayesian version of this has been studied by Andrea Goldsmith and Anusha Lalita. So they used Thompson sampling. And again, so they combine their posteriors by exchanging information with neighbors. So they are able to show again that this achieves the right log T scaling or some log T scaling. So these are all with classical multi-arm bandit problems. Then you can consider extensions to more complicated models such as contextual bandits. This is a natural extension to look at. So going back to the restaurant example, now the contextual information may be your preference for different types of cuisine. So that comes into your rewards. And so, Abhishek and Roshi and Sanjay looked at this as well. Really interesting and challenging problem is what to do if there are malicious agents. So what if somebody lies about what's the best arm? How much can they corrupt your estimates? To some extent, the intuition is that our algorithm should be fairly robust to this, because while we do take recommendations, we don't necessarily follow them. We try the arm that has been recommended. So somehow it shouldn't affect things too much, but it can also be bad because if you constantly keep getting new recommendations, your arm set may not stabilize, and so that could have a negative impact. So they came up with some ways to deal with this. So those are nice results, but it's also quite a heavy algorithm. So there might be scope here for trying to come up with simpler and more elegant algorithms. So that there's open problems there potentially. Then there's a whole line of work I didn't talk about at all. It's not in the bandit context, but might be interesting also in a collective decision-making context. So, the model here is that, again, agents choose from a finite set of arms or actions, but the rewards are now conditional on some true state of nature. And so it's a bit like contextual bandits in some sense. So this was a model proposed for stock traders, so the people were interested in, is there herding in stock markets? Are stock traders efficient as classical economics would like us to believe? Or are they influenced by others and simply follow others? And the empirical evidence on this is mixed. We still don't know whether stock markets are efficient or not. So whether there's herding on. But anyway, so in this case, agents receive noisy private signals about the state of nature. They don't share the signals, but they take actions like buying a stock. So what you observe is just the actions of other agents, and you have to use that information to learn the true state of nature. And then you can ask questions like how quickly can you learn the true state of nature in the setting. Okay, and so there are also open problems in this area, but that's not something we looked at. Some other open problems closer to the spirit of what we looked at. Yeah, I mentioned this already. Our additive constant is huge. A better analysis could maybe help to reduce that, and maybe better algorithms as well. So we looked at also the setting of finitely many arms. A natural extension is infinitely many arms, a continuum setting, but then some kind of unique smoothness, maybe Lipschitz or the continuity of the rewards. So that's an open problem. And okay, instead of regret, you could also think about best arm identification. So that's another interesting problem. And everything I've done is for stochastic bandits. I'm not very familiar with adversarial bandits, but I think extending any of this to that would also be a nice open area. Thank you. Stop with that. Questions?
the stars versus cycle example that you mentioned, which one has better conductivity?
The star has better conductance.
Okay.
Still works.
Yeah, that was.
I have one question that is like, feel free to divide for offline discussion. Like, are there any works that looks at the case where there is a kind of restriction of agents can play certain set of things? This is like on top of this setup.
I guess you, at the very least, you have to allow them to play the best arm, otherwise you're in the limit. Additional restrictions, I don't know. I don't know if much will change. If everybody is allowed to play the best arm, hopefully it will still spread by gossip in the same way. And some
Maybe
other.
then the regret will, like the regret benchmark should be also updated. It is not captured and it cannot be achieved as well. So the best possible offline actions will be the benchmark.
Yeah, okay, if not everyone is allowed to play the best arm, then you have to change that.
I mean, like best within its own subset.
Yes, yeah.
So if there are no further questions, then let's thank Ganesh again.